We'll conclude this module with OpAmp circuit applications. As you know, OpAmp circuits are fundamental building blocks in a wide range of signal processing applications. Examples of signal processing applications especially includes instrumentation. That is, we're going to look at an example of interface design dealing with transducers. Then we're going to have an example of status monitoring, which is related to the previous one. Process control, such as proportional, integral, and derivative control, PID controlling. Filtering operations. Analog to digital conversions. And then we'll start off with an example of digital to analog conversions. The first application is digital to analog conversions, or DAC. Here we know that the DAC is a mixed signal device with a multi-bit binary input. So here we have a 4-bit input in this example, where B1 is the most significant bit and B4 is the least significant bit. So we have a 4-bit digital input, goes through this conversion process to yield an analog output, VO. And we also, part of the input is a V reference signal. So here, V out, in terms of this block diagram, is governed by this following input, which we have a digital input, and an analog output is governed by this relationship here. Now B1, B2, B3, and B4 in this example is either a 1 or a 0. And you can see here that VO is a combination, a weighted combination of these bit inputs. So here B1, B2 has half the weight, B3 is another half of the B2, or 1/4 of B1, and B4 is 1/8 when compared to the bit input B1. So these are the weights, and that's how you get an analog output based on this weight. So once again, B1 is the most significant bit and B4 is the least significant bit, which carries the smallest weight. So let's look at an example of this. Let's say, and K is a constant, so let's say K is equal to 0.5, and our reference voltage, our maximum voltage, when we have all ones in our bits like B1, B2, B3, B4 is a 1, then this V reference will be the maximum, and it will be at least 1 bit less than the maximum voltage. So in this case, let's say V reference is 10 volts. Let's say we have a digital input of, we have B1, B2, B3, and B4, and let's say our input is 0, 1, 0, and 1. We'll take these digital inputs, this 4-bit digital input, and substitute it in the above relationship here. So VO is equal K is 0.5, V reference is 10 volts, and then we have the following substitution: 0 plus 1/2 plus 0 over 4 plus 1 over 8. All I did was substitute 0, 1, 0, 1 in this equation here. So this yields 5 volts times 1/2 plus 1/8, and this yields 3.125 volts. Let's do another example. Let's try 0, 1, 1, 1. So VO in this case would be 5 volts, 0 plus 1/2 plus 1/4 plus 1/8, and then we should have a higher voltage since the associated digital input is higher than the previous one, and this yields 4.375 volts. And then finally, let's look at 1100. So VO is equal 5 volts. 1 plus 1/2 plus 0 over 4 plus 0 over 8. And that should yield a higher voltage. And in this case, we have 8.75 volts. So that's how we implement this conversion from a digital input to an analog output. And then next we're going to take a look at the binary weighted summer. But before we do that, let's look at the resolution of a digital to analog converter. Now with a 4-bit converter, there are 2 to the 4th, which is equal to 16 possible input codes, and hence there are 16 possible analog output levels. The full-scale output of a DAC is defined as the output when the input bits are all 1. So when it's all 1, that's our full-scale output of the DAC. And in this case, when it's all 1, we see that 5 volts, 1 plus 1/2 plus 1/4 plus 1/8 will give us our maximum voltage of 9.375 volts for this example. The resolution of a DAC is defined as the change of the analog output caused by an input change of 1 bit. So a change of 1 bit is basically 0.625 volts in this example. In other words, 0.625 can be derived for 1 bit when we have 0.001, which is just basically VO of 5 volts times 1/8, or 0.625 volts. So we can think of the resolution as the voltage increment between adjacent output levels. And that's what we mean by the resolution of a DAC for this example. Now we're going to take a look at 2 OpAmp circuits, but that will be discussed in the next video, and we'll just give a quick introduction of just what they're called. One is known as the binary weighted summer, shown here, and I'll discuss this in the next video. And the other one is known as binary weighted summer as well, except we reduce the number of components, and this is called an R2R ladder network. And this will be discussed again with the next set of videos, and we'll analyze this circuit in more detail. So that's basically our 2 OpAmp circuit configurations.